Test, 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 test. Should we start?
I just see sorry, the last update of the presentation
Oh, the last one.
for next week. Okay, I made a change for it. Maybe, for example, after you finish the lecture, show you and update the entire class about the
Perfect. This is for the schedule, right?
Yeah.
Okay. Okay. Yeah. Right. All right, guys. So welcome to the 7th lecture. So today I just had important meeting with the dean office. Sorry for starting this a bit late, but hopefully it will be a very interesting lecture. So this lecture and the next lecture, I think next week as well, will be very interesting research direction for those who would like to work on changing the memory device itself. So we already studied how those DRAM devices work, what is the internal architecture, and what do we need to access data, right? However, this is really not fixed. You can play with that. And we will see a lot of example how you can exploit the operation that we discussed. For example, activating a row, reading data, and then pre-charging it. This order is really not fixed. You can play with it because the memory controller is responsible for sending those commands, right? To get the address, to get the data from the DRAM, and so on. So you can play with the order. You can play with the number of rows that you want to activate before even reading them. So you can activate more than one row, for example. We will see a lot of interesting research paper about that, how you can perform computation inside the memory device. You don't need to bring the data to the CPU to do computation over there and generate results, okay? Hopefully that was a motivation for you to just pay attention. So we discussed last time a lot of things about the fundamentals of the DRAM device. And we said if we look at the top-down approach for the memory device, we start always with a channel. And the channel is the communication between the memory controller and the DRAM device, okay? What is next in the hierarchy? DIMM, which is basically this one. So what you see here is the DIMM device itself. And then out of the DIMM, we have rank. Rank is basically a group of chips, okay? So each of those black pieces, we call it a chip, and the rank could be a group of them. So in this picture, it might be all of them in one rank or two ranks and so on. We will see this example in a few minutes. The rank consists of chips, right? And then each chip has banks. Each of those banks has subarray, which is a collection of rows, or a matrix, right? And we said the granularity that we can access those chips or banks is rows. Excellent. Who said that? So the granularity we can access. Excellent. So we can access all the time the complete row, the entire row. Even if we need just small bit of it, we still need to access the entire row. What's next? Columns. Then we can play with it. However, we still need to access the entire row first, and then we use multiplexer, for example. We provide the column address that we would like to get, and then we can fetch those pieces of information. What is after that? What is the smallest building block? Cell. Excellent. So the DRAM cell consists of 1 and 1. What are those? A DRAM cell, a capacitor to store the charge, and transistor. Excellent. We need a transistor to control the charge. We don't really have to always keep a charge there because a charge means 1. However, the capacitor could store 0 or 1. So that's why we need the transistor, which is the MOSFET transistor, right, to control the charge, when to allow to go through the capacitor and when to discharge it. All DRAM chips in a rank has something special. That's why we have a category called rank. What is that special thing? We discussed it last time toward the end of the lecture. There was a very nice example of how we can fetch the data from a rank. And we said at single clock cycle, we can get one information from single chip. So each of those chips can work at the clock edge. And whenever you get a positive edge, they give you something, right? However, that's why we fit multiple of those chips, right? So at each positive edge of the clock cycle, we got something out of every single chip in the rank. And that will give you collectively 64 bits, okay? So the single chip can give you only one piece of information from single bank. However, if we have multiple of those chips that share 3 things, then they can provide you that the same piece of information, but different data at the same clock cycle. What are these 3 things shared between all the chips within a rank? Excellent. That's one. Instruction, we call it control, yeah. And so data and commands. What else? Address. Excellent. So these 3 things normally shared. I think I have it after the example. But these 3 things normally shared between the chips of the same rank. If it's different rank, then it's not shared. That's why in the single clock cycle, all those chips can know that I want that address in that particular bank, so I can get back all these data. All right. To make things clear, I'm repeating this exact same example that we see together in the last lecture. So here's the cache. I would like to get a cache block from the DRAM device. And here what we have is a rank, so single rank, okay? And all those are chips within the rank. So whenever we have a clock cycle, we said all of them are still sharing the address, the control, which is the command to read or write, right, or to activate a row and so on, plus the data itself. So when those chips return data, all of them sharing the exact same bus. That's why you can see over here, bus, which is 64 bits, shared among all these chips. All right, now I want to move a cache block. But I have here 64 bits. The cache block size is 64 bytes, which means 64 times 8 bits, right? So I can, at every clock cycle, get only 64 bits from the DRAM. So what should I do? So I send a clock cycle. I also send commands to these chips, and they will give me the exact same location in all chips. So I cannot selectively choose different addresses for this chip, okay? And this is extremely important to have the data that you would like to get on the corresponding location, all of them. Although the data is different, but the address should be exactly the same. So now I activate the same clock cycle, and I got the data in that bank, in this chip, in that bank, in this chip, and so on. All of them give me the 64 bits, and each of them gives 8 bits. Okay, so in total, I need 8 of those chips to give me the 64 bits. So I got 8 bytes, right? That's 8 times 8, and that's 64 bits. and I still need more to satisfy the entire request. So I send the next clock cycle with different address this time. The address is the same in the row, but different in the column. So I still need to fetch that row. However, we discussed last time, if the row is not changing, what should I do? I already keep that row in the row buffer, and I don't need to close the row, so I don't need to return it back. So every time I'm requesting row 0, it's a hit. It's not a miss. So I'm saving a lot of time by not closing the row. I'm doing the pre-charge, right? So I'm accessing the same row. However, the column address is different this time. So using the multiplexer, I can change or switch between the columns of the same row. Now I got the next 8 bytes and keep going until I get the 64 bytes. How many times do I need to do that? 8 times. Excellent. Because each time give me 64 bits, and I need 8 of those. So how many clock cycles, basically? 8, right? Because those chips work at every edge of the clock cycle. So I need 8 times, which means 8 clock cycles. This is the picture I promised. So assuming all of them are placed in the same rank, so you can see the commands is shared here, which is basically the command and the address, and we have the data over there. Okay. So they share the 3 things as we discussed, and this way, it's really important to maintain the scalability. So we said at each clock cycle we get only 8 bits, and imagine if we are operating on single chip. This is a really small amount of data, how we can satisfy the requests of all the caches in the same time. And this is why we have the many chips in the DIMM. Okay. Of course, we can increase that number. However, we cannot increase the throughput. That 64 bits is really fixed. Why? How many of you see this in real life? Are those something that you can imagine, or really physical pins? Physical pins, right? That's why we cannot change it. So that is the interface, what we call an interface. And this thing is really placed in the motherboard. So if we want to increase the number of pins over there, we have to change the motherboard itself in order to get more data at the same time. That's why even if we increase the number of chips, we cannot do anything with the throughput. We still get 8 bits per chip per clock cycle. But at least we can fit 8 of them within a rank. Now that is for single rank. We can, of course, have multiple of those ranks, and each of the rank have 8 chips, for example. In this way, we can get things in parallel. So as we do housekeeping for the first rank, after we fetch the 64 bits, we can prepare the other rank to do something else. This way, we can overlap the computation. We will see a few examples of that. This is the architecture. And the previous lecture, all of these things were cartoon examples, right? But this is where you can see the actual architecture from inside. That is a single DIMM, and we have 8 of those, starting from 0, 1, all the way to 7 chips. You can consider them the same rank, so we can align with the previous example. The things we can see inside the chip is several of those banks. Now, with a single bank is basically a matrix of data or cells. So each of those cells store single bit. And to access a row, we need the row address decoder, so we know in which row we are operating. And then we have a row buffer, which we call it. What do we call the row buffer? Sense amplifier, which is doing 2 jobs. First, sensing the value when we activate a row. And the second thing, it's activate or amplifying the signal that we got from the row. Okay. Now here, of course, we need the column decoder, so we can understand which column we want to fetch from the row. And then we can send that 8 bits that we got from the column to the data bus. So here we have 64 because it's already shared among all the chip. You can see 8 bits, 8 bits, 8 bits, and so on. Hopefully it's clear. The advantage, yes. So from the user, he really doesn't see these things. He doesn't even work with the memory controller. So he has a program. The program needs some operand, some data, right? And you don't manage anything. The last extent that you can deal with this thing is to write the program. Based on your program, you can change the way it acts, right? So based on your program, you need some data to do, for example, multiplication operation, right? You have two operands, you multiply them, you have a result. These two operands, you need them from the storage. So you bring from the storage to the DRAM, to the caches, all the way to the register and the CPU, or ALU operation, right? Now, who's doing that for you? Memory controller is one, operating system is another thing, okay? Those two things are trying to manage the entire memory hierarchy for you. You don't have any intervene with this hierarchy. You don't say, please fetch this piece of data from the memory hierarchy or the storage, okay? Does that answer the question? Perfect. All right. So the advantages of having multiple chips is the scalability, basically. So instead of relying on 8 bits only, we can increase that to 64. Now, why we cannot exceed the 64? We already discussed that. Because the interface is really hardware, it's fixed. And if we want to change it, we have to change the motherboard. We will see example about DDR5, how we move from DDR4 to DDR5, which is one of the old standard of the memory to the current standard of the memory. And we change the interface in the recent one, so it's not backward compatible. So if you have motherboard does not support DDR5, you cannot do it. You cannot have those recent memories. Now, one of the disadvantages of having this kind of architecture is accesses cannot be smaller than the interface width. So even if you need 8 bits, you still need to communicate with all those chips in single rank, okay? So we said you have to access the entire row from each bank, right? And now you have to access the 8 chips together. Even if you need a single piece of information from only the first chip and only from the first bank, you still need to access all of these. And we discuss in the cache lectures that we do that on purpose because two things. We always care about temporal locality, right? And spatial locality. What does it mean? We bring intentionally more data in a hope that we will need this data later on, right? Very soon. And also we bring more data, hopefully the data that we requested, the nearby data, the surrounding data around it, we are going to also need it very soon. So those are the two concepts of the memory hierarchy. And we do that really in purpose. So we did that intentionally, basically. All right, now hopefully you are clear about the single DIMM. Now, what if we want to add more DIMMs? I'm sure when you open your tower in your computer, personal computer or laptop, you'll see several slots in the motherboard to fit more than one DIMM. So you can extend the main memory, right? Now, how we do that in real life? So here's single DIMM, right? This is DIMM2, DIMM3, DIMM4, and so on. So you can build, for example, unlimited number of DIMMs. And that unlimited number is really restricted by the number of slots you have in the motherboard. So if you go with motherboard, that is for personal use, normally it's limited to 2 or 4 slots, right? But if you go to server grade, you'll see many of those. Now, how to communicate? So we said there is a memory channel that communicates between the memory controller and the DIMM itself. So imagine if we have 50 of those DIMMs. Now, how many channels do we need? You can go with 50, but that is really bad design. Then the motherboard size will be really huge. It's no longer a personal computer. You could do any kind of topologies for the network. One of them is mesh network. How many of you are aware about mesh network? This is one of the topologies where you can connect network between multiple nodes, right? So you can use that, for example, to reduce the interconnects. And remember, interconnects is really expensive all the time. So interconnects, it's currently a bottleneck and a problem in most of the architectures because it consumes a lot of energy to transfer data from one point to another point. And we give you some hints about the energy. What kind of technology do you use to transfer data from one point to another point? What do we call the system? If we have several data paths, want to transfer them in single link, what do we do? Kind of compression. What do we call it? Excellent. Around that, but what do we call it? SerDes. Serializer. And then at the receiver side, we deserialize that, right? Why we call it serializer? Because they were in parallel in the beginning, right? And then we convert them into one link. That's why we serialize all of them from parallel to serial and back from serial to parallel again. However, this structure you can see over here is just research. It's never been implemented in any of the computer architectures because, again, it's very expensive. And instead of having many of those DIMMs, most of the work in the industry try to improve the DIMM itself. So instead of having 50 DIMMs, now how about we increase the density of those chips in the DIMM itself? We make the banks bigger, for example, the chip bigger so we can fit more data, for example, and so on. So it depends, because again, whenever we talk about caches, we have limited space. So we cannot make the caches bigger. We saw the important example that I try to emphasize all the time, which is L4 cache. Someone could ask, why not just adding more level of caches? That would make things better or cheaper or and so on, right? But we saw one of the examples, which is really implemented in the i7 processor, or i9, was it? I think i7, right? So in i7, I think 5055 HQ, right? Maybe. Yeah, so in that processor, we didn't see any benefit with the L4 cache, except in 2 points, right? Whenever the workload or the data I want to bring from the RAM match the size of the L4 cache. Only in this case, we can see some benefits. All right, so how we can address that? We don't want to build that topology of the network, and we still want to have more DIMMs. So we told you that personal computers motherboard normally can accommodate 2 or 4 slots for main memory, right? How the computer or the CPU can act with those DIMMs. So we said every single command dealing with the DRAM should go through the memory controller first. So memory controller is really orchestrating all those commands with the memory device. Now, if we want to have 2 DIMMs, if they share the same channel, then that's a problem. Why? Because we cannot communicate with more than one DIMM in the same time. So we have to serialize the request to request from DIMM1 first, and then we go to DIMM2 and we got more data. Why is that? Because the channel is shared among them. Memory controller is one. The channel is shared. So that's why we can feed data from one side until that request is already serviced. Then we can go to the other DIMM and we do the things. Now, to solve that issue, we could add, as you can see here, 2 memory controllers. Where is the memory controller located? Please, everyone, close laptops. Everyone, close laptops. In Harvard, now it's mandatory to avoid laptops in classrooms. I'm going to suggest that here in GSU. Please close all laptops, all of them. I see 3 people in stock market, maybe 4. Yeah, please close it, close it, close it. Okay, excellent. All right. So to address the issue of having multiple DIMMs, we can add more memory controller. So now we can isolate the request into 2 DIMMs. Those are really separate from each other. And this, we can ask the memory controller, the first one, to communicate with the first DIMM. The second memory controller can communicate with the second DIMM so that we can have 2 requests in parallel and getting data at the same time from 2 DIMMs. Now we got 64 bits from here, 64 bits from there, and that is 128 bits. So this is improving the throughput or the bandwidth, right? However, it's expensive because we need first to change the CPU itself, because the memory controller is located in the CPU. Okay? If we need to add 2 memory controller, that is an overhead to the area of the silicon itself. So we need to change the architecture of the CPU to do that. And then we need 2 physical channels to communicate with the DIMM itself. Is that clear? All right. This is another way of looking at it. So you have 2 memory controller in the processor. You have 2 channels. You communicate with 2 DIMMs. They have 2 ranks, for example. Remember that you always can activate single rank in the DIMM, but you can always work with multiple chips and single bank in every chip. Hopefully, this mindset of working with the DRAM is now clear, because this is really important once we visit the research paper talking about changing the mechanism of how you deal with the DRAM device. Okay? Remember, whoever dealing with the memory device is the memory controller. A memory controller, you can think about it as a program. It's really a software. It's telling, activate this row, get me this address, give me this piece of information, and so on. So you can play with the order of that program and make something else. All right? So the DRAM chip itself has multiple banks, normally 8, but there are some architecture where we have 16 of those chips. Banks share command address data bus. The chip itself has a narrow interface. Narrow interface meaning that I'm fetching the entire row. Remember that I cannot get smaller than a row, right? But what I get at the end as output is only 8 bits. So that's why we call it narrow interface. From bigger, we go to smaller interface. Now we have the options. We have a lot of DRAM chip that give you 4 bits, not 8, 4 bits. There are chips who give you 8 bits and 16 bits, okay? Now remember, the interface is 64 bits. It's really fixed. You cannot change that. If you want to have the chip that provide you 4 bits, what do you need to do? The interface 64 bits. That's what you get at most per clock cycle. And that single chip now can give you 4 bits. So how many of them you can fit to give you the 64 bits? So now we move from 8 chip So in this way, we can change or increase the number of chips. Okay. My internet connection is not stable. Why? Hopefully, people on Zoom can hear me. Is it muted?
Yeah, I can hear you.
Okay, perfect. Thanks, Jahan. Jahan got an accident, so we wish him full recovery soon. Are you in the hospital?
No, there was not that much of major injury. I
Okay.
have
Glad
some
to
pain
hear
in the
that.
body, that's why.
You missed chocolate, but take care.
Yeah, I think hopefully in the next class.
Thanks a lot. All right. So now we move from general DRAM architecture. Now let's see in closer look DDR5, which is the recent one. We said this is currently the latest version. We don't have DDR6, for example. But if you hear DDR6 and DDR7, it's still relevant, but we discussed last time, it is about graphics. It's about GPUs. So in GPUs, you can see up to DDR7, but they call it GDDR7, okay? And remember the difference between GDDR and DDR is only the number of pins in the chip itself. So a single chip, instead of giving you only 8 bits, they give you much more than that. This is what you see from Samsung. This is real DRAM device, DDR5. Has the same latency as DDR4 and DDR3. However, the throughput or the bandwidth here is much higher, okay? The maximum DIMM capacity goes from 64 gigabyte to 1 terabyte. The maximum capacity of a single chip is 32 gigabits with a bandwidth of 6,400 megabit per second. And each chip has 32 banks, okay? But remember, we can activate only single bank in a chip. Now, I told you about the story of changing the interface. Okay, you can see here there is a slight change in the interface that makes it really huge difference in terms of the motherboard. This is DDR5 in the top. You can see the division over there is really in half. So the right side and the left side are really half, right? But in the older version, there is a longer side than the other side. This is shorter and this is longer. But over here is really half. Okay? This is how you may know that this is DDR5 and this is DDR4. Is it clear? Yes, please. So I'm not sure that's really a valid, strong question, why they had it in the first place in DDR4 like that. So I think it started from the older version. So DDR4 is already compatible with DDR3 and 2 and so on. But the change, why they made it in 5, that is maybe a better question, why they have to change the interface, okay? Excellent. So I think why they changed the interface into DDR5, I don't know what was wrong with DDR4, why they have longer side than the other one. Okay, that's one thing. But why they make it in DDR5? So they split the channel, which is the 64, into 2 sub-channels. Okay, so in terms of the design or architecture level, they try to improve that internally. So it doesn't make any difference for us, except the fact that now they have more bits over there, and they increase the number of bits for the ECC. Okay, so it's 64 bits in total. We have 32 for one sub-channel and 32 for the other sub-channel. They also add a number of bits for what we call ECC. We will see it in a couple of slides, and we discuss what is ECC. Error correction code. Okay, it's related to Hamming distance, where we transfer data from one point to another, and then we have a mechanism to detect how many errors or differences between what I sent and what the other side received. Okay, but that was a great question. Now we'll see other component in the middle. So first of all, this green thing, we already saw it in the first lecture. You remember what is it? PCP. Excellent. What is PCP? Printed circuit board, which is, you can think about it as plastic, right? Where we have all the modules inside it, and we have some traces over there to do some kind of communication between the chip and somewhere else. Okay, so you can see there are some thick lines over there. Maybe here it's much more clear, and those lines are connecting the chip itself with the data path and so on. Okay. However, in the DDR5, it's not only about the interface. The changes were really fundamental in terms of the other component over there in the middle. Let's see the first one. So this is maybe a cleaner picture. This is from different company. The previous one from Samsung. This is another company. And you can see the interface much more clear. Here's the front side. This is the back side. All right. Here, why they divide it into equal halves. So you can see the interface. This is where we have the 64 bits, and it's divided into 32 bits over here, 32 bits over there, and some bits for the ECC. That's in total give you 80 bits. Okay. Now, in terms of the component in the middle, the first one, what we call a management module for managing the IC. That is something let's not worry about. However, there's something very important, which is the clock driver over there. This is one of the added module. There's another thing here called the hub. A hub is important for these two sensors. This is TS, means temperature sensor. Temperature sensor. Why we have 2 in each side? Why not just use one of them and that's it, right? Why we need 2? Sorry? High availability. Do you remember Tesla self-driving car? Why we have 2 processing chip? Excellent. It was for trusting the self-driving car, right? In case one of them fail for whatever reason, the other one working exactly on the same data in the same situation and so on. Here, why we have 2 temperature sensors? Now we are dealing with very critical problem, which is impacted by temperature. You remember what is it? What is it? Why? Why? To maintain the voltage, what do we need to do? Excellent, excellent. That's called deserve 2 chocolate, not 1. That's a very important point. So you see how he correlates the temperature? Is 1, 2. Excellent. The refresh rate that we have to do for all banks, all rows, and all chips is really impacted by the temperature. Okay? So if the temperature of the DRAM module increased, we have to cut down the time for refresh into half, meaning we have to do it much quicker. So every once in a while, we have to refresh everything. And that's consuming a lot of energy. So it's really important to monitor the temperature. That's once the energy is thing and how to do the refresh. The second thing is that if we are late in doing the refresh, what will happen to the data? We're going to lose it because these capacitors, remember that, they leaks over time. So we are losing the charge that is stored inside the capacitor, meaning that a cell that is storing a full charge, it's going to be a 0 because that charge is going to reduce over time. So we move from 1 into binary 0. That means totally different data. And you can imagine what will happen to the entire DRAM module if everything becomes 0. Now, okay, we still didn't answer why we need 2, not 1. Yeah, temperature is important, but still, this is a very small piece. Why the temperature will be changed from this side to the other side? Why the reading over here might be different from the other side? Different channel, but still, like if the temperature here is increased, probably will impact something in there. So they did their experiment, okay? You can see this is a real figure I got from the data sheet of one of the DDR5 module. So it's really important to go through the data sheet and start to read it, okay? But you can see over here, they said once you fit the DDR5 in the motherboard, there are some kind of cooling system. We discussed several of them. We said heat sink, right? Some fans, some nitrogen, some air cool, and so on. Now, all of them will be located in one side in the motherboard. If you look into the fan, where is it always located? In top of the CPU and also next to the power supply, right? At the back of your tower. Not sure if there's a tower here. I don't see it. But probably somewhere, you can trust me. You can look if you have a tower, personal computer, right? Normally the fan is located in one side, but it's not near the DRAM module itself. It's not near the GPU and so on, right? That's why the airflow will go from one direction to another direction. It will be cooler over here, but warmer over there. That's why the temperature will be really different from one side to another. And that's why we really need 2 of these temperature sensors. This one will be higher, and this one will be cooler. So now we could, for example, we may want to refresh those at faster rate than the other side, if the temperature here is much higher than the other side, for example. Any question? However, those temperature sensors are optional. Not all DDR5 will have them. Okay, that's why we have the hub over there. If you want to activate them, you probably need to add additional feature to the hub, and then you can enable the DDR5 to activate the temperature sensor. In all server grade DDR5, we have both of them activated. But in personal computer, normally they are deactivated by default. Okay, because really the temperature in personal computer wouldn't go that high. So bandwidth is external thing, right, between the DRAM and the CPU. So all of these are managed internally, right? So we could send this information to the controller so the controller know when to refresh, right? But it is not going to impact the 64 bits of the data, for example. This is about the module that's responsible for the clock management. So you can see several of them. For example, there is the clock acknowledgement. This is the management for the IC itself. And you can see the clock over there with the reset. This is the channels, channel A and channel B. This is the row. These are the ranks, for example. And you can see the clock if you're interested in knowing the frequency of it and so on. But this is like, it's really technical details about the chip that manage the clock generation inside the memory. And why we talk about clocks here? Do you remember the serializer, deserializer? So if you convert the 8 into 4, you go with a slower frequency, right? And now when you want to transfer the 4 into 2, you go with faster frequency. And 2 to 1, much faster frequency than the rest of the module. That's in serializer. That's why you need 3 different speeds, basically. So the first one, you can consider it as F, and then 2F, and then 4 times the frequency. So this one will try to squeeze the 8 into 4. This one will squeeze the 4 into 2 path, right? So if, for example, the signal is this way, and this is 1 clock cycle, right? And you have 8 of them, you can repeat as many times as you wish. This one will try to compress this into half of the cycle. So it will be converted into something like this. So half of this. And when you have this one merged over there, so this way you fit 2 of them into 1 clock cycle because of the faster frequency we are using. Now we convert the 8 ones into 4 in this way. Now in here, we have to squeeze more. So we have to fit more data in the single path. Okay. So now we transfer this. We transfer this clock cycle into this shape. So we squeeze more. Now we take this clock cycle, we squeeze it over there. That's why the frequency over there go double, double, double. So who's responsible for that? Is the clock generator in the DRAM module itself, okay, to transfer the data through a single path. Now, another important feature in the DDR5 is the error correction. And this error correction, you could see it as additional chip in the DDR5. So if we said the rank itself has 8 chip, so you will see 8 chip at the left side, 8 chip at the right side, and then you will see additional chip, and that's responsible for error correction. Okay. Now, this kind of really top secret for companies. They don't tell you anything about it. It's really hard to know what's the architecture, what is doing, what is correcting, and what kind of algorithm, what kind of error being corrected, and so on. But there are some research on reverse engineering this chip. They do the error, they introduce themselves, and they see the result, how they correct them. They do that with too many patterns, and then observe the output, whether that is, for example, just single error correction, multiple error correction, and so on. One of the very important problem with the errors is we have 4 papers in the schedule about the exact same problem. What is it? Who's reviewing security paper? Security paper. No one? Security papers. We have 4 of them. Who's reviewing Rowhammer? Who has Rowhammer in title? 1. Who's else? Okay. That's not good. We already have the 4 papers assigned. Okay. So I was thinking to explain a little bit about Rowhammer, but when I saw the 4 papers chosen about that topic, then I said, okay, there will be enough speakers about the topic. So Rowhammer is basically when you activate one row in the DRAM and you activate another row that is nearby the first row, and you do that very quick, like you activate this, let's assume it's row number 1, and you activate row number 3. It's not right next to it, but nearby, okay? Now keep activate this, activate that, activate this, activate that. What will happen? This is going to impact the data stored in row number 2. In row number 2. It's going to really alter the bits stored there. Why is that? Remember, all operation happening in the DRAM is analog. You have capacitors, you have voltage going through this, and because the density is getting more and more as we move with the DDR5, so we try to fit more capacitors in the same size of the chip, right? That's how we increase the capacity, and we make it from 2 GB to 4 GB to 16 GB and so on. So basically, we fit more capacitors in the chip itself, meaning those 2 rows are really nearby each other. So anything happening here is going to impact the nearby rows. And by doing this really quickly, you're going to erase the data or to flip the bits. If it is 1, it will be 0. If it is 0, it will be 1. And this is kind of hacking the hardware because you are hacking the data itself, right? You are altering the data itself. There's what we call a Rowhammer defense mechanism. So in recent DRAM chips, we already have this mechanism implemented in the ECC itself. That is one of the hack or the attack that we can solve. However, until now, there are a lot of research showing that it's not solved yet. They could solve it in certain scenarios. For example, if you are targeting to activate the same row repeatedly, then the ECC is going to block your request for some time. It's going to impose some relax between the requests. Because this Rowhammer attack happened only if you activate that row and then you activate that row in a certain time period, if you do it really quick. If you do it slowly, like you activate that and then you wait a few minutes and then you activate that, it's not going to impact the victim row, okay? So one of the ACC mechanism is just to block the user from requesting activating nearby row within time period. So they can delay that time frame, preventing you from doing it quickly. You can still fetch the data because they cannot block you from not getting data at all, right? But they can delay that request so you can activate that row, then access somewhere else, then supply the request for that row, okay? We will see that hopefully in a few talks. I'm sure there's 4. One of them there, okay. All right, so we talk about different setup for the interface of single chip. We said a single chip might give you 8 bits, but there are other chips that give you 4 bits. There are other chips give you 16 bits. So you can think about different combination of those chips. For example, if you have a single chip that is 16 gigabit, so normally the chip itself, the size or the storage, we measure it in bits, not in bytes, okay? But the DRAM itself, we measure it in bytes. So this is important to differentiate between bits in here. That means a single chip and the DRAM itself, the entire storage size over there. So if you have 16 gigabits chip, you can make 4 of those. So that will add up into 8 GB. or 24 gigabits of chip, 4 of them will make 12 gigabytes and so on. So then you'll have 16 bits coming from the first chip, 16, 16, and 16. That's in total 64. So that's like different configuration that you can choose yourself. If you have a chip that provide 8 bits, so you can have 8 of them instead of 4, because the total should at the end be 64 really. And here you have different configuration, depends on the capacity of each of those chips, but you always have 8 of them. So you can multiply that number with 8, you will get 16 gigabytes. You could have also 16 of them, but in here you have more than 1 rank. Okay? Remember, it doesn't matter. If you have really 16 of them, it's still you can access only 1 rank. So by the end of the day, you will access only 8 chips of those. Okay? That's why in total you should get 64. So it doesn't matter if you have 1 rank or 2 ranks, but it matters only when you overlap the accesses. So you access the first rank, you get something from it. Now this rank try to pre-charge or try to do any housekeeping. Then you can access the second rank as you are doing housekeeping in the first rank. In this way, yes, you may increase the throughput, but not doubling it. Okay, you may overlap some cost and reduce the thing. Hopefully this is clear. Now this is one of the architecture where you have single rank. So again, you can have 8 of those chips. Each will provide 8 bits. Again, that is all design choice. You don't have to deal with it. You don't have to change it. You cannot change it basically. Only the manufacturer can play with those design choices. Now you can see those DRAM chip in the both side, in the front and the back side of the DRAM. In these two cases, we have single rank. In this case, we have dual rank. But remember, each of them will operate not at the same time. Okay, so it should be sequentially sending 64 bits first, and then another 64 bits. All right. Now a very important topic: how we improve the memory performance. So we discussed how we improve the caches, for example. Do you remember how we improve the cache performance? How did we improve the cache performance? By optimizing look-ahead addresses. For example, speculation, right? So we speculate the instruction that they are going to need some data later on, and then we fetch those in advance, for example. Excellent. What else? What could we change in the cache itself? Replacement policy. Excellent. We change the policy to optimize it for increasing the number of hits, for example, or optimize it for increasing something else. For example, we saw different example on isolated misses, right? Or misses in general, how to reduce those misses. What else? N-way associativity, right? You want to divide the cache instead as one plate, putting everything in one plate. No, you have 2 plates, 3 plates, 4 plates. Okay, so you can organize the thing and reduce the number of hits rather than randomly assign blocks to the cache. All right, that was excellent. Now, how to improve the performance of the DRAM device? So in order to improve something, we need to know what makes it better, or how we measure a performance metric over there to say that this is now better than previously. So the DRAM performance is defined by the bandwidth and latency. What is the bandwidth? So these are 2 important metrics, bandwidth and latency, to measure the performance of the DRAM device. What is bandwidth? Speed in transferring the data. Not only speed, but should be also amount of data at which we send it, right? So at the speed where we send these data, it means amount of data divided over time, okay, per second. And normally we measure it as a mega transfer per second. Now, what is latency? So bandwidth, we could send like 64 bits every once in a while, for example, right? That is a bandwidth. But now the latency itself, what if, how we make the things faster? We access the same row repeatedly, right? But with different columns, for example. This way we save a lot in pre-charging. So we open the row, we access it. Now next time we access the same row, but different columns. This way we can make the latency very minimal, although we still access column by column every time. How we make the latency higher? By accessing different rows. We access the first row. We now pre-charge it, closing the row. Now we want to activate another row, right? So we want to bring it to sense amplifier, read it, send it to the data bus, and then pre-charge again. That's latency is different than the previous scenario, for example. And the previous one was shorter because we didn't do pre-charge to every request. We are reading the exact same row, but different columns. So latency is basically when I send requests from the memory controller to bring me the data, and then when I get the data, that's time for round trip is the latency itself, which is the delay in which the memory device is going to supply me with the data that I requested, or the time it takes for the memory controller to receive a response after requesting data from the DRAM. Is it clear? All right. Increased bandwidth, if I'm increasing the speed at which I send data, it means higher latency. Why is that? If I'm increasing the bandwidth, the amount of data I'm sending at the same time, it means higher latency and increased power consumption. The power consumption is clear because whenever I increase the frequency in the interconnect, I always need higher frequency to squeeze more data. If I'm getting this data, not in this clock cycle, but I'm shortening the clock cycle, for example, in here. If I shorten this clock cycle even a little bit, I have to change the frequencies right away, okay? Because I need to make it now double of that amount. And then double, 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 all the way until I satisfy the one link. But why higher latency? Why when I increase the bandwidth, I increase the latency? Excellent. Or what if I change the row size? Now the row size becomes larger, right? Imagine I change the architecture of the DRAM. I make the row larger, and the chip now is providing, instead of 8 bits, 16 bits, for example. What will happen? I need a decoder that is larger, right? That's in terms of number of columns because I increase the size of the row. But also if I increase the number of rows in the chip to fit more data, to increase the capacity, I also need to change the decoder to decode the row where I need to fetch the data. But not only that, I also need to increase the size of the row amplifier or the row buffer, the sense amplifier, right? Increasing all those hardware would require more time to fetch more data, right? And also it's expensive, reducing energy and so on. But also, you could increase the number of chips, for example, to provide more data. Imagine that, forget about the interface, the 64 bits. What if we increase that interface and want to increase more chip? That will also cause to increase the latency, although all of them operate in the same clock cycle. But now that clock cycle is going to change, okay? This is an important figure showing the progress in terms of capacity, bandwidth, and latency. What do you expect? Is it always increasing, decreasing? Think about the DRAM you have in your computer, how it was 10 years ago. What was the size? Very small, like 1 gig in maximum. Then it moves to 2 gig. It moves gradually to 4, 8, 16, now 32 on that range, right? So it's always increasing. How about the bandwidth? It's also increasing, right? Latency, reduced. Now, which one is faster in terms of improvement? Remember the example, the difference between the bandwidth of DDR4 and DDR5. Was it doubling? You remember the figure we show in last lecture, where we moved from DDR4 into DDR5? We see that there are very little improvement in terms of the bandwidth. So the capacity is really improving almost linearly, and it's getting even cheaper, right? But the bandwidth is almost saturating. The latency is a little bit increasing, but in very smaller pace compared to the capacity, for example. Why is that? Remember in the first line when we mentioned about DDR5, we said the latency is almost the same as DDR4 and DDR3. Okay, so this is important to keep in mind. The latency, there is some point we cannot get much of improvement on that. We try to increase the number of capacitors, but by the end of the day, the interface is restricting us from getting more data as we want. So we are limited by the end of the day by only 64 bits. So the latency to send those bits in the interface is almost constant among all of them because they are using one channel and we are accessing the same number of DRAM chip and all of them accessing single location in a bank and give us all those data, okay? Same as we did in the cache. So in the cache, we were improving a lot of things. For example, the number of sets in the associativity, right? Or we could increase the cache itself, the capacity size. Same in here, we could increase the bank size. We could increase the row buffer or improving it, sensing more. We could utilize advanced process node to enhance efficiency and speed. So advanced process nodes related to the transistor level itself. We said at each cell, we need a capacitor and transistor. And transistor could be smaller, so we could fit more cells, right? Increasing the size of the interface. This is not happening until now. We are only increasing now the more bits for ECC, for example. But we're still dealing with 64 bits until today. Can we increase it more? Can we make it 128? Could be. Yes, please. Yes.
It has 4 DIMMs for RAM, but it was not recommended to do so. One of the reasons is that either do so by buying or or their own how format. So I both channels, what would be
Excellent question. Did you understand the question? So you are allowed to add 4 DIMMs into your motherboard, but it's not recommended to do so. It's recommended to double the size of single DIMM rather than adding 2 DIMMs, for example. It's better to double the size of the 2 DIMM rather than adding 4 DIMMs to the motherboard. Why is that? Why it's better to have a larger capacity single DIMM rather than having 2 DIMMs with half capacity and half capacity? For example, you have 8 GB in one DIMM. You purchase another 8. You purchase another 8, another 8. Which one is better? To have 4 8 GB DIMMs or single DIMM with 32 GB? Single one is better. Why? So first, there's congestion in the data you get from several DIMMs. The first thing you have to understand how many memory controller first we have in the CPU. Okay, if we have multiple, this will make things way different because each of those will be isolated system. So you can communicate with all of them in the same time, and you get data from all of them at the same time. So we don't have any issue here. If we have single memory controller, what will happen? You have to get data from here. All the rest are idle, doing nothing. Although you add them, you pay money for them, but they are doing nothing because memory controller can communicate only to this, wait, get data, communicate to this, get data, and so on. Although you can overlap many of the things. So you start from the first DEM, the clock cycle, right? You send a request from memory controller. Maybe you get the data at some point here because there's always latency to service your request. Now, within that time, after you get the data, you need to pre-charge, right? You need to refresh that row because you already perturb the row itself. You already alter the data itself. So you can, while waiting for those housekeeping stuff, you can send another request to the other DEM. So in this way, yeah, you can overlap some of the time. So you don't really need to wait the double, like waiting for the first DEM to service your request fully, and then you ask for the other one. But the benefit you get compared to the price you pay is really not that beneficial. That is one thing related to the outside world. Now, if you look into the single DEM itself, what will happen if it is really larger capacity, meaning that it fits more data, meaning that you might need the same row again and again. So you activate one row, it's already in row buffer, and now you're going back to get the same data again. So you will find it most of the time because it's already in the row buffer. Now, if that data does not fit in that row, and your DEM, for example, is small in capacity, so the rows might be smaller, or you have less number of rows, then you have to access multiple banks or multiple chips or multiple DEMs to get larger data, right? In this way, you are also losing some benefit or some opportunities to improve the accesses. That was a fantastic question. Thanks a lot. So that's the beauty of this course. You will see most of these things really in your computer, in your own life, once you deal with that. Okay, any question? But remember, all those optimization, we call them optimization, but in fact, they are really design choices. So only the one who can change these things is the manufacturer itself, the company who produced the DRAM. And it's not only that, but also will have significant impact on the DRAM system cost, because changing the capacity, adding more chip, more channels, more memory controller, and so on, it's all going to impact the silicon area that you are consuming. All right, so we always keep saying this is design choice, this is the company can do it, but how they do it? So this question is from the book that we recommend for the course. Do you remember the name of the book? What is the name of the book we are using for this course? Who are the authors of the book? Maybe that's easier. Patterson, excellent. Who else? Hamming? No, not Hamming. Yes? Wow. The other one, Patterson. Yes, that's correct. The other one. Oh, Patterson is more famous than the other guy. The other guy was president of Stanford. So that's a homework for you, okay? One of them in Google, one of them the president of the university. So please check this question in the book. You can copy the text and you will find it in the book. This is really kind of debate. Which one is better? To have a chip in the DEM module giving you 8 bits or 4 bits or 16 bits. Now remember, we need 64 bits all the time. So if we have 8, that's going to dictate the number of chips. So we need 8 of them. If we have 4, we need 16 of them. If we have 16, we need maybe 4 of them or 2. 2. No, 4. 4. Who say 2? 16, 16, 16, 16. That's 64, right? Okay. So which one is better? By the end of the day, I'm getting 64 bits, so it doesn't matter in terms of bandwidth, for example. Remember, those separate chips, right? Really isolated from each other, although they share the three things. Since they are in the same rank, they share the data, the address, and the command. However, each of them requires certain amount of energy. So each of those has its own energy consumption. Now, that is a very important metric, because if I add too many of them, like 8 of them or 16 of them, and they consume much more than what I have in 8 bits, that's going to consume a lot of power in terms of the total DEM. And then to consume the power that the entire motherboard is consuming, and probably it's going to affect the temperature of the motherboard and so on. So to answer this question is really not easy. You need to know the internal of this chip and how the clocking is connected to those and so on. For that, you can access this Excel sheet. There's a link in the book, but the link is not working anymore. If you open it, you will not see it. Okay, it will point you to Micron, which is one of the companies that's producing this DRAM. So I updated the link for you. This is updated one. You can open it. You will see several sheets, several Excel files. Okay, you can choose based on the technology. You'll see DDR1, DDR2, 3, 4. There's no 5, unfortunately, but you can at least choose 4. Right? You'll get an Excel sheet. In the Excel sheet, you'll see a tab called configuration. Based on that configuration, you can choose those numbers and send me the screenshot, what you'll get as a result out of it. So you just play with the configuration. It's automatically update the things internally. You'll see a lot of sheets in the Excel, and you'll see all the numbers get updated, and it will give you several parameters about the cost that you are going to pay for each of those designs. Okay? It will ask you a lot of questions: how many pins you want, how many chip, how many bits out of each chip, how many banks, and all of these questions. So feel free to play with it and send me a screenshot. You may get a bonus out of it. Okay, not a chocolate this time, but a bonus. Who likes chocolate? All of you, right? Who likes extra grades? All of you. Okay, maybe we can do both. Depends on how many students will send that screenshot. All right? I think so. I think so. I think so. So the interface is standard, right? But the parameter you send, it's really different. For example, we talk about refresh rate. Who's doing the refresh? The memory controller. If I need to do it faster, then the memory controller should do something to send more requests, right? And remember, when I send refresh command, it means the memory controller is blocked from sending any instruction or any command. Cannot send anything for that period of time because the DRAM is busy doing the housekeeping stuff or refreshing all rows, right? So of course, it's going to impact the memory controller or the CPU. And they should to communicate together for having correct workflow. Any question? Any questions so far? Yes. Extra? Raise your voice, please. Yes, yes, that's favorable, but you can still have the 2 or 3 or 4. You may get some benefits. Where's the figure? I think this one, because we are going to overlap the requests to get the data. So it's not like you need to wait for the first DEM to be fully processed and then you ask the second DEM. If we have multiple things, each one will have a cost. So when there are bandwidth, then we increase this, then we have other things. Excellent question. Excellent question. Did you understand the question? So your classmate is asking, if we have 16 gigabyte, one DIMM, is it better to have another 16 or just replace that 16 DIMM fully, remove it, and add 32 gigabyte? Okay. Now he's saying that the DIMM is operating in its own clock cycle, right? And the other DIMMs also work on its own clock cycle, meaning that they are independent. They can work like really at the same time, and each of them provides 64 bits. That's 128 bits per clock cycle, which is better than having a single DIMM with larger capacity that only gives me 64 bits again, right? Because the same interface. That's a very strong question, very valid one. But that is also go back to the CPU architecture. How many memory controllers do we have? If there's one, how many channels now do we have? If there's again one channel, I cannot do anything about it. Even both of them give me data, where to place that data. I should place it through the channel. Now the channel only fits 64 bits at the time. So I have 64 bits from the other side, but it cannot fit. So I have to sequentially push it. The first 64, then the second 64. I cannot have both of them at the same time. Unless I have two memory controller or two channels, right? You remember the mesh topology? Then I can alternate between the DIMMs. I get this one, then this one, or both of them in the same time if the topology allows for that, right? So if you have two memory controller, two channels, it solves the problem. It doesn't matter now. Doubling or having two of them, it's still the same thing, same effect. You can access both of them in parallel, and maybe it will be much better than even doubling the size. Okay? You understand the question? You understand the answer? This is really important. Okay? That's why I show you all those pictures. Although might not be relevant to the course, like you're not really designing this DIMM, but it's really important to understand how it works, and I'll leave everything else to your creativity. So you can come up with your own architecture, assuming that everything is correct, you can fetch the data in the correct time, and so on. And this is how you start doing research in memory device. You have to understand what is happening in the DDR4, and then you can change anything in it. You literally can play with the device. You can do whatever you want with it, okay? Assuming you maintain the parameter for activating a row, charging, discharging, and all these parameters. We discuss about ref, I, which is refresh interval, right? This is one of the parameters that you need really to meet when you build your own system for the memory device. So there's a certain amount of time where you need to send requests every interval of those time. You have to send a request, stop sending other requests, wait for the DRAM device to do the refresh rate, and then you can continue doing so. If you do that, everything is correct. Then you maintain the correct data in the DRAM, and so on. Right? So hopefully you'll do this exercise. This is for you. There's no correct or wrong answer. As long as you insert like correct information in the configuration, then you should get the correct answer. Other way of improving the technology, you could replace the DRAM with SRAM. But we know the problem with SRAM, right? It's very expensive. If you want to replace the 64 gig with 64 gig of SRAM, you have to pay a lot of money to do that. Other memory optimization. The first one, hopefully we know by now, which is loop row major, right? Row major approach, which is loop interchange. So if you want to access a matrix, we know that the C language, do we have it somewhere? Maybe we don't have it yet. Yeah, C stores multidimensional array in row major order. So it's all related to the C language, for example. C language, try to store your data structure in the memory in a row fashion. And we already know now, we already discussed it for caches. Now we are not discussing caches. We discuss how row major is going to also improve the memory performance. So why do you think it's still valid for memories? We discussed why it's valid for caches. Why do you think loop interchange is going also to improve the memory accesses? Not Naim. Not Naim. Why do you think loop interchange could improve the memory performance? We'll discuss why for caches. Yes, please, Mansoor. Yeah, but why accessing data in row fashion is going to be much better than column-wise? But the same thing for columns. If I want to access columns, I need to activate a row and then access certain amount of data. Why accessing a row is better than accessing column? You don't have to change. Excellent, excellent. You understand? So by accessing the first row, right, all the data in that row already exist in the same row. Although you access column by column, but you don't really have to pre-charge again every time you access the column. Now, if we access column-wise, what will happen? So the first part of the column exists in a row. So you're going to access that row, pre-charge, finish from the row. Now you move to the next row, you want to access only the first part of it because you are accessing the entire column now. You access another row, you bring only the first part of it, you access another row, and so on. But once all your data in the same row, then you access that row, you keep it in the row buffer and keep switching between columns. And that's much faster than closing the row, accessing another row, and move on. How about this? We'll discuss it for caches. That is blocking. What does it mean? So this is a matrix multiplication. Do you remember what's matrix multiplication? How many of you? 1, 2, 3, 4. The rest are sleeping. We have 4 sleeping heads. Okay. Yeah. So matrix multiplications basically bring a first row, multiply it by the first column, and the result will give you one cell. Now the first row with the second column will give you this cell. The second row with the first column will give you this. The second row with the second column will give you that. Okay. So that is being said, there is no row major, there is no column major. What's happening, I'm accessing rows from here, but columns from the other matrix, right? So how to restrict myself to only rows, for example? I cannot do anything about it. There's a mix of rows and columns. I cannot keep it only rows, cannot keep it only columns. In this way, we can reduce the cost. For example, instead of accessing one column at a time, meaning that for every row, I need to access the entire row from DRAM, right? Access the entire row, bring only the first column, move to the next row, bring the first column, and so on, right? Instead of doing that, I could go for more number columns. So you access the first row, but bring like 5 columns, for example. Now it's much better than bringing only the first column. Go to the second row, bring 5 columns. Go to the third rows, bring 5 columns, and so on. Now you still have other columns because you bring only 5. You can go again to the row 0, bring the next 5, second row, bring the next 5, and so on. Now why this is better than accessing one column per row? It's kind of amortized cost, right? It's a bit reduced. It's not like wasting the entire row, and it's not like utilizing the entire row. It's somewhere in between that. And this is where the concept of blocking, which is basically get only this portion, which is first row, 3 columns, second row, 3 columns, do the same thing over here, the same thing over there. And then you calculate part of the solution, part of the solution. That's somehow a mix of both approach, row major and column major. But maybe you could ask yourself, like, we are accessing the rows over here, but we are accessing the columns over there. What if we just flip the matrix, right? What if we just rotate it and we make the second one as row-wise? So this will be the first row, this is the second row, right? Then the two matrices will be like row-wise, and then problem solved, right? And then we can access the things better granularity, so we could access the rows, right? Would that solve the problem? Why? Yeah, of course, that can be changed, right? But in terms of memory accesses, we already improved the things because we are accessing the entire row instead of one row and fetch smaller number of columns, and then the other row, smaller number of columns, right? That's one of the way of doing that. Now, who's managing the data layout in the memory? For example, it might take some time, but do you remember the example where we fit cache block from the memory to the cache? This one. I'm asking the memory to give me a piece of information, and that piece is really relevant. Imagine that I need one operand for one multiplication. So you have like x times y equal z. So this is operand times another operand, and this is the result, right? So imagine I want to fetch this entire matrix, and this is a huge matrix. It could be like million by million. Okay? Now, how to access this matrix in very fast way? How to access this matrix in very fast way? Imagine this is really huge. Like 1 million times 1 million. Could be a billion, trillion. Now, we know that each chip will provide you only 8 bits. How to make the best out of that architecture? You need to divide, like one row will get 8 bits out of it. So you need to divide those 8 bits into a chip, the second 8 bits into another chip, third 8 bits into another chip, such that when you access the entire row, for example, you access it in the exact same time from all chip altogether. So that being said, meaning that I need every 64 bits of the matrix to be divided over several chips. In this way, I can access those entire 64 bits in the same time. So every time I send for request, I get 64, 64, 64. That's for the entire row. Would be that better, or having the entire row in a single chip in the single bank row? Which one will be better? You understand the question? You want to get that row, you want to store it in a single chip, in a single bank row, like this entire row will be the first row, or you want to bring every 64 bits of that row and divide it equally over all chips, such that in a single clock cycle, you get the 64 bits all the way at the same time. We will see that in a few minutes. Okay. This is a really important question. But who's doing that? Who's dividing your data over chips or over banks or over DIMMs or over channels or over memory controllers? Who's doing that? Operating system. Excellent. Did you get chocolate today? I have a lot of chocolate. All right. Yeah. Now you'll see the answer. Please pay attention. There's a very important topic called memory interleaving. Memory interleaving. What does it mean? the memory controller assigns consecutive memory addresses across memory banks. Okay. A data that is next to each other, the memory controller tries to assign that data when we bring it from the storage, for example, right? From the storage to the memory, try to assign it across memory banks. Okay, so try to divide over memory banks. Now, those memory banks could be in the same chip or could be over multiple chips, right? And that will be different interleaving. Now we will see both of them. We'll see even a third case. Interleaving can occur on the same DRAM chip as we see in the example. Do you remember the cache example? This is very important. Or across banks in different chip within the same rank. Now, this example, you'll see how we divide the data in the same DRAM chip, but over multiple banks. So imagine you have a data block. The data start from here, which is 8 of those rows, 8 rows in the bank, right? Whatever the size of the row. So you could divide them equally, and we call this division 4-way. We call it 4-way because in the first way, we start in bank 0, then 1, 2, 3, and then iterate. So whatever the size of the matrix that you try to fit in the banks, you just bring whatever you could fit in the first row, you move to the second bank, third bank, fourth, and then iterate. So if you have 1 million, you could divide it, for example, 200 bytes in the first row. You could fit that amount in here, then there, and you continue doing that. That's what we call 4-way interleaving. Okay. Now you could do it also over multiple chips. So here, all of them bank 0, but chip 0, chip 1, 2, 3, you could do the exact same thing. Now we ask ourselves, which one is better? Let's see it together. Now, if we do it in different DRAM chip, what will happen? Remember, in one clock cycle, we could access all chips. Each chip will give you 8 bits in the same time. And this is what will happen. So we access bank 0 from chip 1. We activate a row. We read the data. We pre-charge. Activate, read, pre-charge. Activate, read, pre-charge. All happen at the same edge of the clock cycle. So all of them happen at the same time. Now, of course, if we have K chips, then we can service K requests. Now, if it is in the same chip but different banks, how many banks can we access in one clock cycle? 1. Excellent. So only 1 bank we can access. Then what will happen? We're going to activate a row, right? Oops, shouldn't see the answer. You missed chocolate. You activate a row in a bank, you read the data, and then you pre-charge that row, right? Now you cannot access any other bank. You stop. You access that chip, that bank. Now you move in next clock cycle with the next bank, next clock cycle with the next bank, and you can see that we overlap the coast. It's not really serialized because we activate, then you can activate another bank and so on. You move on. At this point, you receive some data over here maybe, or here. You receive the data, then you receive data over there. You receive data, data, data. So there is no conflict in the data bus, okay? But you overlap the coast to pre-charge the rows because it's independent anyway. So you don't care about other banks, what's happening over there. Now, which one is better? You want to do it in one clock cycle, or you want to do it over, I don't know, maybe double the time. So this will finish over here, and this maybe finish over there. Or you can calculate it from the time you send the request all the way to until you get the data, maybe, so you can forget this part of it. But still, much longer than what we have in the first case, right? So it's all about how you divide the data layout itself. And there is a lot of research how you can accelerate one application by just playing with the data layout. Whether your matrix want to flip it this way or do it that way, or increasing spatial locality, temporal locality, and all this stuff, okay? A third case of interleaving, which we already discussed several times, when you have two memory controller. Now, how you divide your data among two DIMMs? It's not single DIMM. So you don't divide your data among chips or among banks, but you divide it over DIMMs. You want a half of your data, for example, to be in one chip or one DIMM, the other half in another DIMM, such that you improve the memory optimization. So you can do exactly the same thing. And here we call it two-way because you get portion of data into one DIMM, the second portion into another DIMM, and you repeat, you iterate. That's why we call it two-way interleaving. There's a lot of question in the exam about that. Assume you have two-way or three-way interleaving. It means you should know by default that there is 3 banks in the DIMM, if I told you that, okay? If I'm telling you that it's interleaving over chips, it means 3 chips. If I told you it's over banks in the same chip, you should know that there's 3 banks in one chip. So even without telling you the architecture, you should know by just knowing it's a 3-way interleaving. I think it's a perfect time to stop over here. We already finished interleaving. So remember these 3 cases. Next lecture will be next week. It will be a very exciting one. You will see how we can perform bitwise operation in the DRAM module itself. We're not moving the data to the CPU, for example. We perform all this computation inside the DRAM itself. Oh, it will be this week, Thursday. So on Thursday, oh, Grigori, you have qualifying exam. Good luck. I'm his examiner tomorrow. Should I bring chocolate? Yeah, good luck to those who are having qualifying exam. I think this week is full of qualifying exams. How many PhD students do we have here? Wow. Do you have qualifying exams as well this week? How many of you having qualifying exam? You're a strong guy. All the best. All right. Yeah, we'll have a lecture on Thursday. Yeah. Probably supper need to announce something about the schedule. We make some changes based on request. So if you didn't request, it's not related to you.